and as it is called in this, Dublin Skeptics in the Exchange. We're usually in the Lord but it's usually a social setting that we go to, and that's where we will be retiring to once this talk is over, because we have to clear the space by 7. So David has very kindly acquiesced to his wonderful talk that he gave to the Cork Skeptics last month on media and statistics. So I'm going to just let you fire away. Nobody came here to listen to me.
No pressure. Talk before 7. Okay, a lot of talking to do. I'm sorry. Hi, my name is Dave. One of my qualifications for being here, none really, apart from someone wanted me to talk, and I'm going to try and do that for the next while. Okay, sure. Teething problems, apologies. Okay, so my background is I'm a doctor of medical physics, and I have a keen interest in skepticism and science writing, which I do a good bit of at the moment. When I was doing my doctorate, something I found really interesting was, really interesting, this is kind of strange, when you're spending all day looking in a journal, you suddenly realise there's a massive dichotomy between what you're reading in a journal and when you pick up a newspaper and read the paper's account of that exact same article you've just read, when your jaw drops and goes, are these people from the same planet? I mean, I'm going to try and give you some examples later on and what we can do about it. But I'm going to start with the most boring part first, and I always apologise for this one, right? We're going to do some numbers first. Anyone here enjoy maths in school? That's better than you graduates. Right, so first part we're going to do, give this math statistics, stat, right? So science and medicine, technology, these are things that concern all of us, right? But the sources of information we get them from tend not to be the researchers themselves. We tend to get them from TVs, magazines, or if you've been on a train anytime recently, the bloody metro, right? Which we'll talk about in a while. Right? But things are very rarely as clear-cut in this field, and the first major obstacle is, I like the statistical one, right? It's the biggest one I see. So here's an article from Fox News, right? Media reports today are focusing on cases of a deadly metavirus, whose effects include a bad thing, another bad thing, and a really awful thing. Right? Thankfully, this disease is rare. Only 1 in a million people get it. And luckily, there's a test that is 99% accurate. Now, you should go and get yourself tested. So everyone runs off, diligently to the... Meanwhile, back in the lab, here's 1 million people. It doesn't really look like 1 million people, but let's say it's a perspective for Right. So they all get tested. The test is 99% accurate. So, what do you expect? You expect one positive person. This is just from the bases, and the rest of them to be negative. Right? That's what you expect. But curiously, that's not what you get. Right? You'd actually get 10,000 positive tests here, just from that 1% error ratio. And you get the one positive guy is 99% certain, it's a good chance he'll get it, right? So you actually end up with 10,001 positive tests, only one of which is positive. So this means the odds of having the disease with a positive test are 1 in 10,001, or 0.0099%. The first observation I want to put into you is the veracity of the test is directly linked to the prevalence of that disease. Your test is 99% accurate. It absolutely is a good test. But because the disease is very, very on the low rate, it gives this kind of idea that we're going to only get a small amount of certainty. We're not. We actually get a lot of false positives with tests like this. Now you might think this is a totally made up example, and it is. So let's talk about real diseases. Anyone here ever got a positive HIV test? There you go. We'll talk about our private lives. Might as well bring it out. A friend of mine did a few years ago. Right? He went in, and now the guy, frankly, was a very unlikely candidate to have HIV. But it's quite common. The blood bank were all the time. And I'm going to tell you why now. Let's look at real diseases. Here's HIV. If you were in a typical low-risk group, and most people are low-risk unless you're shooting up that often, the Western ink blot ELISA test is about 99.99% accurate, so even more accurate than my hypothetical one, and only about 1 in 10,000 people will have it from a low infection. Okay? So what actually happens with that? So here's 10,000 people with no known-risk behaviour, low-risk people. One has HIV, 9,999 do not. Right? So the guy who has HIV, or the girl, I won't be sexist on this, turns out to gets a HIV positive test. It's a very good test. The odds are he's going to test positive. Right? How about the remaining 9,999? Well, one of them will get a positive test, just because of the accuracy is around the same size as the sample group. So you now have 2 positive tests, only one of whom has the disease. If you have a positive HIV test, even with that test, your odds of actually having the disease are 1 in 2, 50%. So it is quite common if you're giving blood to get called back in to be flagged in a false test. It does happen, and it has happened to. However, let's look at the other side of the coin. If you had people who are high-risk group, say drug users, their base infection rate is 1.5%. So you expect 150 of them in 10,000 to have it. So, of the 10,000 people with known risk behaviour, 150 have HIV, and 9,850 don't. Of that test, they all test positive. The test is that accurate. They're going to test positive. And 0. And however, if the group that don't have it, one of whom will test positive. So if you did have HIV with a positive test and you were in a high-risk group, your odds of actually having it would be 150 over 151. So 99.34%. Now this is something I want to ram home a little bit. With statistics, without a reference class, the accuracy of your test means absolutely nothing. And this is, and we're going to see how in media this tends to skew things royally, okay? Because without that reference class, without knowing how many people have the disease in the first place, you can have a test that's 99.9999999% accurate, and it means jack. It means nothing, right? Luckily, we do have epidemiologists who know what the prevalence of the disease is and know how accurate the test is. But strangely enough, medical doctors get this wrong all the time. And I love doing this on some of my doctors I work with. I love asking them these questions and watching their answers. I go, what's the odds I have HIV with a positive test? And they go, oh, 99.99%. And you go, ha, wrong, doctor. That's what I do anyway. So here's colorectal cancer. So about 30 in 10,000 apparently healthy people, and this is asymptomatic people, will have it, right? The standard test is, I said I wrote fecal there, that's wrong. That's right. Fetal was, I had a typo in it before, which would be blood in your baby, which should be strange. But fecal occult blood syndrome doesn't mean like haunted blood, it just means blood that shouldn't be there. Like, oh, that shouldn't be there in my stool. So if you have that, there's a 50% chance you'll test positive for this, fecal, and if negative, 3% will test positive. So you have 10,000 people in apparently good health, 30 have the disease, and the remainder do not. So if you do the test on all those people, you'll get a 50% chance if you have it. You'll get 15 who are FOC positive, fecal occult blood positive, and 15 who are FOC negative. I like saying that. In the other group, you'll have 300 who are positive, and even though these are all negative people, and not negative people, but you don't have the and the rest, right? So this is weird. This gives you a really weird diagnostic. If your chances of having this disease with a positive test are only 4.8%, or 15 over 315, your chances of not having it, so your chances of having it if you get a negative test are 15 over 9485, which is 0.00158. So as diagnostic tests go, that's a pretty shit one, right? I wouldn't want to. You might think that's one of them. In fairness, they'll do other tests on you if they think you have. We now have scanning devices and machines, and I know about them that can go up your colon and just. We don't want to get into it. That's a different discussion for another day. So I swear the maths is almost over now, and then we get to laugh at the Daily Mail. That's great. So, why does this happen, right? You've got specificity, which is the number of true negatives over the number of true negatives and false positives. So a test with a high specificity will have a low rate of false positives. And you've got the flip side of that coin, the sensitivity. The sensitivity is the number of true positives over the number of true positives plus false negatives. So a test with a high sensitivity will have a low rate of false negatives. Now, let's consider the case for HIV again. The specificity was 9,999 over 10,000, which is 0.9999, and sensitivity was 1 over 1 was 1. If these are high values, then why does this test only predict with a 50% accuracy? That doesn't seem to make much sense. The problem is small incidence. The test has both high sensitivity and high specificity, yet the odds of having the disease are even less than the accuracy of a test. Did anyone here study physics? I imagine kind of like diffraction. If something's almost the same size as something else, you get scatter effects. That's a really nerdy way of describing it. I'll never do that again. I'm sorry. So what you can express it is with a positive predictor value, a PPV, and there's a converse, a negative predictor value. A PPV is a number of true positives, number of true positives, false positives. So in this case, the PPV for HIV would be 1 over 1 plus 1 would be 1 over 2, 50%, exact same as we calculated. Conversely, the negative would be 9,999 over 9,999, would be 100%. So if you get a negative with the HIV test, you're in the clear. But if you get a positive, you only have a 50% chance of having it. It's mad, isn't it? So, conclusion, blah, 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 blah. Yeah, let's see if the maths come on. Okay, the other problem, and this is where we start getting into media territory, is conveying risk, right? So here's, you can't really read that because I picked a terrible font. Here's a study abstract. People with high cholesterol can rapidly reduce the risk of death by 22% by taking pervastium sodium. So how did they work that out? Well, here's a study they did. They got thousands of people, obviously, and the ones who were taking this pravastatin, they worked out 32 died, and the people that were taking the placebo, 40